Thank you very much, Claire, for that wonderful introduction. And it's, of course, a great honor to become a honorary fellow of the Cambridge Philosophical Society. When I arrived in Cambridge in 1976, the weather was worse than this, I remember, and even though it was October. But one of the very first things I did was to join the Cambridge Philosophical Society. So a few years later, to now become an honorary member is a tremendous honor for me. Very good. So so what I'm going to talk about is cosmic extinction, the far future of our universe. And I don't want this to be, in spite of the weather, a gloomy lecture. So even though cosmic extinction is inevitable, as we will see, it is going to happen in a very, 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 very long run. So we don't need to be gloomy today. On the contrary, I'm going to show you some of the most amazing advances in our understanding of the universe in a little while. So this talk has two parts. In the first part, it's rather local. It has to do with extinction and survival, just in our own neighborhood, in our galactic neighborhood. It's going to be the first part, and then in the second part, I'm going to jump ahead a little bit and tell you about what the long-range future of our whole universe looks like. So just for those of you who are not physicists or astronomers, just a little bit of notation. So the first piece of notation I'd like to introduce is a light year. And a light year is not a unit of time, it's a unit of distance. And it is the distance, that light travels in 1 year. Light travels very fast, so in 1 year it travels 10 trillion kilometers, which is about 100 times the size of the solar system. Now, and because of the finite speed of light, then we see astronomical objects not as they are today, but as they were when the light was emitted. So, for example, in the rare occasions when one can see the sun, which doesn't happen very often, in Cambridge we're not seeing the sun, or the light of the sun as it is at the moment we see it, but because it takes 8 minutes for light to get to us, we see the sun as it was 8 minutes ago. So the downside of this is that in astronomy, we're always dealing with out-of-date information. We're always dealing with information of events that have already happened. The upside, of course, is that we can see into the past. So we are the only scientists, reputable scientists, that have the ability to look into the past. And essentially, when we look at, for example, very distant galaxies, then we can see them when they were much younger than they would be today. So in astronomy, we have this great bonus that we can study evolution for free. We just need to contemplate what's happening, and we can get a picture of the evolution of the universe. Now, so the building blocks of the universe are galaxies. These are collections of stars, up to about 100 billion stars. We live, of course, this is not a picture of our own galaxy, but one very similar to our own galaxy, and we live about 2/3 of the way from the center of the Milky Way. Here's my building. My colleagues in Durham, they still think that they live in the center of the universe. I keep telling them every day, no, the center of the universe is not in Durham, it's in Cambridge, but they still want me to show you a nice building of the institute where I work. Now, so to get you, and I should say the size of a galaxy is about 100,000 light years across. So if you send a signal from one end to the galaxy and you expect a response from the other end, you better be rather patient, because it's going to take at least 200,000 years for our colleagues at the other end of the galaxy to respond to us. Now, to get you in the right cosmological mood, I want to show you a movie. I wonder if we can turn the lights down. So this is a movie of real data, and which will take us in a journey around our cosmic neighborhood. There's only one little bit of artistic impression. All of it, apart from that bit, which I will point out, is actually based on what's really out there. This is a movie made by a colleague from the University of Hawaii, Brentoli. Right, so we're going to start this journey by just looking out from Earth. Many of you will recognize the Orion constellation here. And next to Orion is a gas of a cloud of gas and dust called the Orion Nebula that you can see here. And these clouds of gas and dust, of which there are many, are the sites where new stars are being born in our galaxy. It's the Milky Way is making new stars at the rate of about 1 to 2 new stars per year. This is the Horsehead Nebula, another place where stars are being born. Now, this many stars, actually, we now know, are born in groups. This is a nursery of stars called the Carina Nebula. And, if you can look, although I don't know if you can see, but there's several stars all being born from the same cloud of gas and dust. Now, not all such clouds are birthplaces of stars. Some of them are the opposite, graveyards. Here is a very famous nebula called the Crab Nebula. And this inside here, there's a star that very similar, in fact, to the sun that has reached the end of its life. And I will tell you how that happens later. And it has left a pulsating object in the center called the pulsar. Now, this is a little bit of artistic impression that I advertised. We're going to leave our galaxy. Of course, we cannot do that. But we'll see a galaxy that's very similar to our own. And this galaxy, our Milky Way, has two very well-known famous companions called the Large and the Small Magellanic Clouds. And they're part of something called the Loco Group. And we're now going to head towards our nearest neighbor, the Andromeda Galaxy, which is about it's about 2 million light years away from us. Here it is. And itself, Andromeda has a neighbor called M32, which has its own clouds of gas and dust where new stars are being born. I say this is about 2 million light years away. And now we're going to take a little tour to admire some of the incredible things that nature has managed to make in our universe. We're going to eventually head to the Virgo cluster of galaxies in a minute, but before that, we'll just take a look at some of these really majestic structures. These are the so-called grand design spiral galaxies. Some are interacting with smaller neighbors that they will eventually swallow. And we're now headed towards the Virgo cluster, which is about 30 million light years away from us. Clusters are collections of galaxies ranging from a few to a few thousand bright galaxies. And this cluster is famous for many reasons. It's our nearest large cluster, but it also, in the center, has a galaxy called M87, which is very famous because in the center of M87, there is what we call a supermassive black hole. All galaxies we now know have black holes at the center, supermassive black hole. So in this particular case, this black hole weighs about 1 billion times as much as the sun. And there's activity going on associated with the black hole eating things that you can see slightly in that jet. So let me continue with my computer until it crashes. And with a bit of luck, it might not crash. So now, so that is what's around us. That is what the universe around us looks like. And one of the questions one might ask, you might wonder how many galaxies are there in the universe? And there are many, of course. There are about 100 billion galaxies in our visible universe, which coincidentally, 100 billion is also roughly the same number as the number of stars in our Milky Way. So the universe is full of galaxies, 100 billion in the visible universe, and each of them, or not all of them, but the typical one, with about 100 billion stars. So when you come across these enormous numbers, the first question you might ask is the question of is the question of where is everyone? Now, that is a question that was asked several decades ago, 70 years ago, no, 80 years ago, by a very famous physicist called Enrico Fermi, and it's known as the Fermi paradox. So Enrico Fermi reasoned as follows. He said, well, any advanced technological civilization will inevitably undertake interplanetary travel. And once a civilization has moved on from its original planet, once it hops to another planet, the technology is there for that civilization to spread throughout the galaxy. And there are so many stars in the universe. Why haven't we seen any signs of extraterrestrial life? So that's known as the Fermi paradox, and we don't know the answer to that yet. Now, one way you might try to go about answering that question is through a simple formula proposed by Frank Drake, who died last year, called the Drake equation. So the Drake equation is a very simple formula that just tells us the number of communicating civilizations in our galaxy. So that's what n is. How many civilizations in our galaxy that can communicate are there? And it's a result of the product of several probabilities. And let me tell you what they are. R star is the average rate at which stars are forming in our galaxy. That's that one. This is the fraction of those stars that have planets. NE is the fraction of those planets that are in principle habitable. F is the fraction of those where life actually arises. Fi is the fraction of those planets that have life, that have intelligent life. This is the fraction of those intelligent civilizations that would wish to communicate with us. And then L is the lifetime of a civilization. Now, so when I became a PhD student here, in fact, we only knew one term of this equation, which was this one, the average number of stars that are formed in our galaxy per year. All the other ones were completely unknown. And it's quite amazing. I mean, it wasn't that long ago, at least doesn't feel that long ago, that I was a PhD student, that in the intervening few decades, we now have a good guess for most of these numbers. Unfortunately, not for all of them. So, but for many of them, we do. So as I indicated earlier, we now know that the Milky Way is making new stars at a rate of 1 to 2 per year. So that we know, that's the first term in that Drake equation. Now, so the fraction of stars with planets. So 15 years ago, 20 years ago, the only planets we knew about were in the solar system, the familiar solar planets. But in the last 15 or 20 years, there's been a real transformation in the subject, thanks largely to the satellite called the Kepler satellite, and which has now found about 3,000 planets in the past 12 years. We know there are we know 5,000, and most of them had been found with this NASA Kepler satellite. Now, the way Kepler finds planets is sort of illustrated here, but let me show you I need to remember it's the down arrow. So let me illustrate how Kepler finds planets. Here's a picture of the sun, and you see now a planet transiting in front of the sun. It will appear in a minute. There it comes. And what Kepler does, amazingly, when you see everything that's going on in the sun, it can measure the small dip in the light that we get from that star as the planet moves across it. So it's a tiny little dip, and it just gives you an impression of the precision with which these instruments work. So it's a very, very small dip in the amount of light as the planet transits, and that's been enough to detect this large number of planets. And now we know, amazingly, that almost every star has a planet around it. So virtually all stars have at least one planet, and about 1 in 6 has an Earth-sized planet. Here's some examples. Of course, on Earth, we have Venus, the Earth, and these are 2 of the other planets, very similar to the Earth that Kepler has found. So the question then is, how many of these are habitable? Now that's a hard question. First thing we need to know, well, what do we mean by life? Now, very conveniently, we have a definition provided by Gerald Joyce, a working definition that's been adopted by NASA of what we mean by life. In this definition, life is a self-sustaining chemical system capable of Darwinian evolution. That seems to me a reasonable definition of what life is. And so with this definition, we can ask what fraction of the planets is habitable. Now, that's very difficult, of course, to answer since we haven't seen life anywhere other than Earth. But we can try to make an estimated guess from what we know on Earth. So here's a picture of the evolution of life on Earth. It all started when the sun formed. The sun is about 4.5 billion years. So 4.5 billion years ago, the sun formed. And then the first billion years were not really a good time for life to emerge because the Earth, and the planets formed at the same time as the sun. The Earth was bombarded by asteroids and the really very difficult to imagine how life could have emerged then. But about 500 million years after the Sun and the Earth formed, the bombardment stopped, and immediately we have evidence for life. So life, in a very simple form, as simple cells called prokaryotes, appeared as soon as it could. As soon as the Earth relaxed, then immediately life appeared. And then it stayed very simple for a long time. In fact, multicellular creatures only appeared about 1 billion years ago. And of course, we mammals and other advanced or complex forms of life only emerged very recently. So, but simple life emerged as soon as it could, and life stayed pretty much simple until about 1 billion years ago, when multicellular creatures first appeared. Now, so what a reasonable guess from that, the fact that life on Earth emerged as soon as it could, must be that most planets must have some form of simple life. And so that seems like, to me, a reasonable guess, that the fraction of planets that are habitable, all of them have life, at least in a simple form, or the majority of them. So that, of course, we don't know for sure, but it seems to me a reasonable assumption to make. Now, but the much more complicated is to answer the question of which of those do go on to develop intelligent life. So again, we need to start by defining what we mean by intelligent life. And I have a definition, which again is a definition. We can argue with the details, but to me, intelligent life should be self-aware. It should be able to understand and learn things, and it should be able to modify its environment. In other words, it should be able to develop technology. So this seems to me a reasonable working definition of intelligent life. And on Earth, at least, it took 4 billion years for intelligent life to emerge. So simple life emerged as soon as it could, but then it took a long time, 4 billion years, for evolution to produce intelligent life. Now, so how likely is that? When you look at the Earth from outside, it looks like a perfectly friendly, hospitable, peaceful place, but in fact, it is anything but that. For intelligent life to evolve, we seem to need, at least in the one example we have, 4 billion years of planetary peace and quiet. Unless, of course, intelligent life has emerged many times and been destroyed many times, which is, of course, a possibility. But having 4 billion years of peace and quiet is not easy, because we live in a very aggressive, hostile environment. I'll show you some examples in a minute. The universe is dynamic, it's changing, and it's very violent. There are very high energy phenomena or events occurring, all of which are inimical to Darwinian evolution. So let me just give you a few examples of events that could have stopped this unicellular life from becoming more complex and eventually intelligent. So for example, I'm going to go through this in a minute. An asteroid impact would not be good for evolution, or it might be good. I'll tell you more about that in a minute. There are other violent activities that could have interrupted evolution. Let me tell you about those. So the first one that comes to mind is a large asteroid impact, because we know that has happened. Here's a picture of a famous asteroid. I feel embarrassed to say that it hit the Earth very close to where I was born, in Mexico. And these, we know, killed the dinosaurs about 66 million years ago. And these happened roughly about 100 million years. It has to be a large asteroid, 10 kilometers or bigger. Now, whether this is good or bad for evolution is not clear, because in this one example, killing off the dinosaurs opened the niche for mammals and eventually humans to emerge. So I'm not completely sure that, that asteroid impacts are bad for evolution, but I think nowadays with the technology we have, even if we might be able to do something about an asteroid if we detect it early enough. So I'm not too worried about those. I am, however, very worried about supernovae. Now, supernovae, I'll tell you more about them in a minute, are stars that have reached the end of their life and they explode. And when they explode, they produce enormous amounts of radiation, such that if we had a supernova exploding close to us within 25 light years from us, then of the Earth, it would be devastating for life, because the radiation from the supernova would essentially would destroy the ozone in the atmosphere, and if the atmosphere doesn't have any ozone, then all life gets fried by the solar radiation. So very likely, if we experience a supernova within 25 light years, then life on Earth would perish. Now, so we don't know how often this is likely to happen. You can see here that we really don't know what it is. We could have one of these once every 100 million to 2 billion years. It's very uncertain, but we know they do happen, and on a time scale comparable to this time scale of 4 billion years that I'm talking about. Now, even more dangerous are gamma ray bursts. Gamma ray bursts are the most energetic events in nature. They occur during the formation of black holes, and they emit in a few seconds as much energy as the sun emits over its entire lifetime. So they're enormously energetic. Now, they are also collimated, and but if we have one of these gamma ray bursts happening within 500,000 light years, that's on this side of the center of the Milky Way. Milky Way is 100,000 light years across. On this side, one of those, and if it happens to be pointing at us, then would strip again the ozone layer, and the UV radiation will destroy all life. So the question is, how often do we expect a gamma ray burst to happen and pointing at us? And we have one of the world experts on gamma ray bursts sitting over there, so I don't know what Martin will agree. I think he does, because I've asked him already. We expect one of those pointing at us every few billion years, where few could be 2 or 3. We don't really know exactly how many. Now, some of you might have, well, I've already mentioned that galaxies have black holes in the center. Now, these black holes are very massive, and they accrete material, and when they do that, they turn into something called an active galactic nucleus. And that is an extremely energetic phenomenon as well, produced, as I say, when gas falls onto a supermassive black hole, which every galaxy, including our own, has one. And so the question is, are they dangerous? Again, we have another expert, Deborah, over there on active galactic nuclei, and I hope she agrees with me that they're not really something to worry about. They're only very dangerous if you're very close to them, within 3,000 light years. Happily, we're about 30,000 light years away from our supermassive black hole at the center, so these we don't need to worry about, happily. Now, another perhaps more exotic danger is the danger of galaxy collisions. In the movie I show you firstly that we have two companions, the Magellanic Clouds. They're on a collision course. They're going to hit us in about 1 or 2 billion years. And even worse, there's Andromeda, which is even bigger than those, and we're also in a collision course with them. So the large and small Magellanic Clouds are the most immediate danger we face. And what will happen when they collide with us, as they will inevitably? Just give them a couple of billion years, and we would have that collision. Now, here's a movie made by my former postdoc, Marius Caltun, of what will happen to the Milky Way. It's a simulation when the large and small Magellanic Clouds come and merge with it. You see, they just get eaten up by our Milky Way. The price the Milky Way pays is it develops a bar. And will these destroy life? And I don't know for sure. One thing that seems very likely is that the collision will eject the solar system from the plane of the Milky Way. So the solar system will be launched to the outer parts of the galaxy, but there's not enough energy in the event to dissociate the solar system. So the solar system as a whole will be moved up somewhere else, but that need not be too bad for life. It'll be bad for astronomy, but not necessarily too bad. So I'm not too bothered by that either. I think the ones we need to worry about are, well, the asteroid, say, that may be actually good for evolution, but we do need to worry about the supernova, the gamma ray burst. This is not dangerous, and galaxy collisions are almost certainly not dangerous. So let's go back here and now ask a hard question, which is this one, the biggest unknown. How long do civilizations last? And that's something that I'm sure everybody here can make an opinion as good as any other. We know that in spite of the beauty of our solar system, or of our Earth, well, and the solar system, particularly at Earth. Humans are a dangerous species, we know that. We read about it in the newspaper every day. And so the end of human civilization could easily be self-inflicted. Before we get hit by a supernova, we have many dangers that we're all familiar with, listed here, some of them, there are more. And so this is the big unknown. How long do civilizations last? Now, so going back then to the Drake equation, we know, as I said, all but two of these terms. We know the star formation rate, the fraction of stars with planets, about 1. The number of habitable planets, call it 10%, 1 in 6. The fraction of those where life arises, I argued, based on our example on Earth, that it should be close to unity. The fraction of those that develop intelligent life is one of the two unknowns. I would imagine that if intelligent life emerges, whether or not they want to communicate, they will communicate. We have been irradiating space around us ever since the advent of radar and television and so on. So we've been communicating already. And if there's life out there farther away than 50 light years, they will know we're here. So I would give that a 1. And then there's this other question of the lifetime of civilizations. And so those are the two big unknowns. Unfortunately, they're so large, these unknowns, that so unknown that we don't know how many civilizations there are in the Milky Way. It could be 0 at any given time. There's at least 1, but we don't know how long we're going to last. Or there could be millions. So unfortunately, because we don't know these two terms, then we really don't know that whether we're alone or not. But I think something that was a revelation to me is that it's possible we're the only intelligent life in the whole Milky Way at this particular time. It's not ruled out. But there could also be many millions of other civilizations. So that's quite a responsibility, that if we are the only form of intelligent life, then if we blow up our planet or we burn it through climate change, well, it doesn't seem like a very enlightened thing to do. Now, whether or not we blow ourselves up or not, one thing is for sure, namely that the sun will disappear inevitably. I already indicated that stars only live for so long. So a star is nothing other than a sphere of gas in equilibrium between gravity and pressure. And in the center, the densities and temperatures get so high that the stars ignite a nuclear fusion reactor. And so stars shine because they're producing nuclear reactions in the center, but the amount of nuclear fuel is, of course, finite. And as stars evolve, or they evolve because they burn through various parts, various elements of nuclear fuel that they have available. They start by burning hydrogen, then they burn helium, and then they keep burning more and more elements until they get to iron. And iron, you cannot get any energy out of iron. And so at that point, when the core of a star like the sun is made of iron, then that's it. That's the end of evolution. There's no more nuclear power available, and the star will then do something fairly dramatic depending on its mass. So for example, if like the Earth, the future of the Earth is illustrated here. I'll tell you more about the Earth in a minute, but we'll inevitably end up with an inert type of star called a white dwarf. I'll show you some pictures of a white dwarf in a minute. More massive stars, more massive than 1 times the mass of the sun, can do more interesting things, like a very massive star can end up collapsing into a black hole after it produces a supernova. So these very massive stars, when they run out of nuclear fuel, the center implodes, and then that energy from the implosion expels the outer parts. That's how supernovae are formed, and they can leave behind the black hole. Slightly smaller stars can leave behind the neutron star, but stars like the Earth, like the sun, will only leave behind a white dwarf. So our sun, oops, sorry, wrong computer. Our sun is a stable star. It's halfway through its life. It has another 4 billion years or so, or 5 billion years to go, by which time it will exhaust its nuclear fuel, it become a red giant, and when it becomes a red giant, it means it'll expand, and it will engulf the Earth, burning everything on the surface. But don't give a sigh of relief, because we don't need to wait 5 billion years. much sooner than that, the sun will pretty much end life on Earth, if there's still any. And that is because of, this is the end of the sun. This is the ejection of the other layers that I promised. But even before the sun runs out of nuclear fuel, in fact, in a mere 1 billion years from now, because it's evolving and the nuclear reactions are such that its temperature will increase only by about 10%. But an increase of 10% in the huge temperature of the sun is enough to boil the oceans from Earth. So in 1 billion years, before the sun becomes comes to the end of its life and becomes a neutron star, well before that, it will heat up enough to boil the oceans from the Earth. And that clearly won't be good for our descendants. So the lesson we learned from astrophysics is we better get out of here. And we have 1 billion years to figure out how to get out of our Earth. And our descendants, if we have any, will have to figure out a way to get out, or that will be the end of our intelligent life. Now, so an interesting question is, well, what will our descendants look like? And here I've learned from Martin Rees, who's sitting there, that he says something that's extremely interesting. He says many interesting things, but in this context, that our descendants, when the oceans are boiled of the Earth, will be as different from us as we are from bacteria. Because remember, 1 billion years ago, life on Earth was all bacteria. 1 billion years from now, our descendants will be as different from us as we are from bacteria. And so what will our descendants look like? Well, Martin again writes about these things. They might be genetically modified posthumans, or, and I think this is Martin's favorite possibility, they'll just be robots, or they could easily be a mixture, cyborgs that are part computer and part post-human, genetically modified posthumans. We don't know what they will be. Whatever they are, they have to get out of the Earth because the Earth is not going to be a place that is pleasant for life. So now I want to, so that's what we know about our local future. Talked about survival and extinction. Well, we will only survive at best 1 billion years, most likely not even that. Now I want to tell you about what our whole universe is going to do. So I want to tell you now about the end of our world. And now I'm going to scale up from stars and the solar system all the way to the entire universe. So if we want to understand the end of the universe, we have to understand how the universe began and how it has evolved. And I promised you at the beginning of this talk that there's been enormous progress in this topic. So I wanted just to tell you a little bit, a glimpse of the progress, how far we've gone in understanding why the universe looks as it is. Now, one of the big surprises of the last 25 years or so has been the discovery that the universe is made of rather bizarre components. Only 5% of what the universe contains is atoms, the atoms that we're familiar with in the periodic table of the elements, that make up only 5% of what the universe contains. 25% is what we call dark matter, which is matter, as the name indicates, that just doesn't shine, that doesn't emit light in any wavelength of the electromagnetic spectrum. That makes up 25%. The lion's share of the universe is something that was discovered only 25 years ago or so. It's called dark energy. I'll tell you about dark energy in a second. Now, first, let me ask the question, well, if we don't see the dark matter, how do we know it's there? And we know it's there because of the wonderful equations of physics, because of the power of the physical sciences that are really so compelling that they allow us to make inferences that are in many ways against our intuition. So this great man who walked around here a few centuries ago, Newton, he realized that matter produces gravity, gravity produces motion. And so if you can, and he actually experienced that motion when He made the error of judgment of sitting near an apple tree. And so if astronomers can measure, as they can, the speed at which stars go round and round the centers of the galaxy, they can then infer from that motion how much matter the galaxy must have. And the big surprise is that there is not enough matter in the form of stars that you can see here to account for the speed of the stars that we see around the Milky Way that we measure. I should say the other day, a few days ago, I was in London near Piccadilly, and I was just wondering about some subtle detail of this argument. I was really lucky. I ran into Isaac Newton himself, and here's Isaac Newton, and it's him. Some people don't immediately realize it's exactly him. It's the same nose, the same mouth, the same eyes, and he explained to me that he'd come back to life, but he said, look, I can't face the life of a modern scientist, having to write grant proposals every month, having to do research assessment. I just can't stand it. I decided I wasn't going to be a scientist, I would be a musician instead. Although he is a scientist, he is an astronomer. It's Brian May, for those of you young ones who don't recognize this great hero of mine. Brian May, he has a PhD in astronomy, and he's also a famous musician. So he explained to me that really we should think of galaxies as being a clump of dark matter that's just holding together this little pool of visible stars. What is the dark matter? Well, we don't know yet because it hasn't been detected, but it's almost certain that the dark matter is some kind of elementary particle that was created in the early universe. The most popular candidate for these particles are called cold dark matter, and they're very different from the particles that make up ordinary atoms. I'll show you some more about this in a minute, even a movie, but before that, let me tell you about dark energy. So I say dark energy was discovered only 25 years ago or so. It's a mysterious form of energy that opposes gravity and is causing the expansion of the universe to become faster and faster and faster, to accelerate. We've known the universe has been expanding for almost 100 years, since the days of Edwin Hubble and others, particularly Georges Lemaitre, who now has been recognized and is now called the Hubble-Lemaitre law. Here's Hubble in the days when scientists were allowed to smoke in their offices, and he discovered that the universe is expanding. And what was discovered at the turn of the last millennium is not only the universe expanding, but the expansion is accelerating. It's getting faster and faster and faster. Instead of slowing down as you would have expected if there was only gravity, there must be some form that is pushing the universe, causing the galaxies to expand at this accelerating rate. That, as is often the case in physics, when we don't really understand something, we give it a good name that will attract funding, and it was called the dark energy. Now, so it won the Nobel Prize in Physics, that discovery, in 2011, and we don't know really much about this dark energy. It's a form of energy, as said, that opposes gravity. It produces a repulsive force, causing the universe to expand at an accelerating rate, and that's about as much as we know. Although we don't know one more thing. Most of the universe is empty. You might have got an idea of that in the movie I show you. Most of it is just completely empty. The galaxies are few and far between. So whatever this dark energy is, it almost certainly has to do with emptiness. It has to do with vacuum, what physicists call the vacuum energy. So whatever it is very likely to have to do with a vacuum, with just empty space. And so that's the dark energy. Okay, so now, so I should say that, right, so suddenly Einstein's equation appeared here. This is Einstein's equation. I'm going to explain it to you, don't worry. And particularly you, don't worry about it. I just want you to see Einstein's equation. It's a beautiful equation because it relates the geometry of our whole universe, of space-time, to what the universe contains. The reason I'm showing you this is because Einstein introduced this quantity called lambda, which in his day he introduced it for completely spurious reasons. But now it turns out that this might have been a really enlightened development by Einstein, because the simplest form of dark energy is this quantity lambda, which is also known as a cosmological constant. So it's some form of energy, and it's constant. Lambda is a constant, and this would be the dark energy if it turns out to be that it is as simple as this. More about that later. Now, so that is what the universe contains. And we now have a wonderful model called the lambda CDM standard model of cosmology. Lambda is this quantity, this Einstein's cosmological constant. CDM stands for cold dark matter. And this model that's been developed since the 1980s has led to really an incredibly compellingly accurate description of what we see in the universe. So let me tell you about this lambda CDM model. It accounts for a huge range of observations from the Big Bang to the present. And so I want to just spend a few minutes telling you about this. Now, do I get injury time because of all the problems we had? Because I just realized I'm running behind. Is that okay? All right. So, in fact, progress has been so enormous that we can make statements and still, as Martin likes to say, keep a straight face, right back to almost the beginning of the universe. In fact, the earliest we can talk about physics with any confidence even has a name. It's called the Planck time. It's a tiny fraction of a second, 10 to the minus 43 seconds. This is the only time in the history of the universe when gravitational and quantum effects were important at the same time. And we don't have a theory of quantum gravity, so we cannot go beyond 10 to the minus 43 seconds. But that's pretty good, 10 to the minus 43 seconds. And in fact, the story really, that as we know it today, begins 10 to the minus 35 seconds after the Big Bang. In 1980, when I was a student here, there was a revolutionary idea proposed that our universe, when it started 10 to the minus 35 seconds after the beginning, that the Big Bang, was in a slightly unstable state, characterized by, again, some form of vacuum energy, which may or may not have anything to do with the dark energy, but some form of vacuum energy that the universe tried to get rid of by expanding very rapidly for a brief period of time. So this is now one of the pillars of our modern understanding of the universe. It has a name. It's called cosmic inflation. And here's how it works. So this is the hardest slide in this whole lecture. So we start here 10 to the minus 35 seconds after the Big Bang, when this period of inflation occurs. It's just the universe trying to get itself into some form of equilibrium by expanding very quickly, shedding that excess of energy that it was born with. This is driven by quantum effects, by subatomic effects. And quantum effects have a tendency to produce fluctuations everywhere. These are called quantum fluctuations. And I even have a movie of quantum fluctuations here. So quantum fields, as may have driven the expansion of the universe, produce small fluctuations. And the fluctuations come and go, and they don't do any harm. But when these fluctuations appear, when the universe is expanding very fast, they get stretched and they become big macroscopic objects. And the amazing proposition of modern cosmology is that everything we see in the universe, all the galaxies, the stars, the planets, even us, started life as a quantum fluctuation of the vacuum. Sounds crazy, and it is pretty crazy, until, as I will show you in a minute, you look at the evidence. So the universe then starts seeding itself with these quantum fluctuations. Then, a little while later, the dark matter, presumably cold dark matter, appears, and the dark matter amplifies these perturbations that are tiny. So it makes them grow by gravity. Show you a movie of that in a minute. So these fluctuations get bigger, and then about 350,000 years after the Big Bang, something important happens. The universe is cooling, and it cools to a temperature sufficiently low that the first hydrogen atoms can form. That causes the fog of the Big Bang to lift, and the radiation, the heat from the Big Bang, is emitted. That has a name. It's called the cosmic microwave background radiation. It's the first light of our universe, and it brings us news about what was going on where the universe was only 350,000 years old, which would be in the human equivalent of 1 day old. So the universe is like a baby at this time. Now, what a physicist, I'll show you how, can make detailed calculations of how the temperature of this microwave background radiation should look like if all this story, in fact, holds true. Now, as the universe expands, it cools, and today this radiation that was very hot at the Big Bang will have cooled down to a mere 2.7 Kelvin above absolute zero. Now, amazingly, that radiation was discovered in the 1960s by these two gentlemen, Arno Penzias and Bob Wilson. Accidentally, as it happens, they just found this very cool radiation, so cold that's in the form of radio waves, of microwaves, and hence the name cosmic microwave background. And they didn't quite realize, somebody else told them that they had actually discovered the heat left over from the Big Bang. So we've known about that since the 1960s, but in 1992, there was a very important development. NASA's COBE satellite made a picture of the temperature of this radiation. So what I'm going to show you is a picture that transformed our understanding of the universe because it showed that the temperature of this radiation is not uniform. It has small fluctuations. They're hot and cold spots. And this map, in fact, made headline news across the world in the days when science was still published on the front cover of newspapers. And at this point, I hope you forgive me. I'm going to leave modesty to one side because I did play a role in here. And if you can see what it says there, it says, Carlos Frenk, an astronomer at Durham University, said yesterday, "Oh, wow." All the cosmologists are on the phone to each other at this moment trying to work out what this means. So this is my great contribution to cosmology, and my wife knows that my epitaph will say, "Oh, wow." It really was an amazing transformational moment because we were seeing directly the consequences of these quantum fluctuations from inflation reflected in the temperature of this heat. So that got George Smoot the Nobel Prize in 2006. The radiation was measured a decade later by another American satellite. I don't have the picture here, it doesn't matter. It was measured 20 years later by a European satellite called Planck. A lot of the work for Planck was done here at Cambridge, not only at Cambridge, these are big international collaborations, but much of the interesting science was done here. And the amazing thing is that already before Planck or before COBE, before Smoot, physicists, in particular Jim Peebles and Dick Bond and George Efstathiou, I don't know if George is here, he might be, there he is. So they calculated mathematically what that pattern of hot and cold spots should look like. I don't have time to explain this plot, just to show you that it has interesting structure. It's not just a line, it's complicated, it's physics, and Jim Peebles, Bond, and Efstathiou calculated exactly what this pattern of hot and cold spots should look like. Now here's a plot that I must have shown, I don't know, hundreds of times to students, to the general public. And I always find it hard to contain tears because this is just so amazing. So let me tell you why. So what you see here is in green, the predictions from the 1980s based on all these crazy ideas about quantum fluctuations, about dark matter, cold dark matter. That is shown here in green. And in red are the measurements from the Planck satellite of these tiny, they're still very small, these signals, they're about 1 part in 100,000. And look at the agreement between the theory and the experiment. And it just seems to me amazing when we're talking about intelligent life, that some form of life happens to have evolved 2/3 of the way from the center of a galaxy, like any other, capable on the one hand of developing the language of mathematics and using it to make predictions for how the universe began, the green line. And this same species of intelligent life is capable of constructing machines that they hurl out of their atmosphere and can make these very highly precise measurements. To me, physics doesn't get any better than this, and I would say life doesn't get much better than this. Now, so that is one of the reasons we know that our model, crazy as it sounds at first, has at least some reality, some description, an adequate description of what we see. So here's a picture of Jim Peebles. He was given the Nobel Prize in physics 3 years ago, not just for that, but for other things as well. And here is George Efstathiou, Bond and Efstathiou. Why they have to carry labels, I haven't yet discovered, I guess, just in case they get lost or something. So these are the characters who have really, and I don't show you, I'm going to show you pictures of all the large number of experimentalists that built the satellite and launched it, analyzed the data. But these are, sorry, George is a friend of mine, so I don't want to say too much about him, but these are sort of my heroes in science because they were capable of making these predictions, which at the time, were speculative and hard to believe until the data came and showed us. Now, so now we know how galaxies began, but they were still a long way. This happened when the universe was the equivalent of 1 day old. So how do we know how these small quantum fluctuations evolve? For that, we need to use computers, and that is something we do at my institute in Durham. We make virtual universes. It's not as bad or as difficult as it sounds. We know this is a beautiful problem in physics because we know the initial conditions, those perturbations that I just showed you. We make some assumption about the contents of the universe, how much dark energy, how much dark matter. Then we know the equations. The equations would be known for a century or more, well, almost. And we just need to solve these equations, which we can do in a big computer. And we have to solve the equations of relativity, dynamics, and so on. And we come back after we let the computers calculate, solve those equations and see what comes out. And what comes out is quite remarkable. We come out with universes that look a lot like the real one. So let me show you quickly a movie. First, just of dark matter. So this is called dark matter. Here's a movie of how a clump, we call them the halo where the Milky Way lives, how it would have emerged out of those quantum fluctuations. Can we put the lights down, please? Is that possible? So you didn't see that because it's too bright, but there were small perturbations. They were the quantum fluctuations from inflation. And what you see them here is growing through the action of gravity. So these small perturbations are unstable. They grow, and soon they produce these amazing patterns of something that on large scales is called the cosmic web. This all came out of this very simple initial state with inflation, which is as simple as it gets. Quantum fluctuations, because of the action of gravity, evolve into this collection of clumps that interact gravitationally. So you see this one being attracted to this bigger lump. So it's going to flow towards it. When it comes to it, it merges with it. Here's another one that wants to join the party. And this is how the halos or the clumps of dark matter where things like the Milky Way live formed from that very simple beginning, from those quantum fluctuations. So I have another 2 movies. So here's what you would see if you were able to travel throughout the universe at much greater speed than the speed of light, and if you were able to see the dark matter. So this is how the dark matter arranges itself in the contemporary universe with a huge range of structures, lumps of all sizes, and that's exactly what we observe, what we infer in the universe. Now in the last few years, 10 years or so, it's been a breakthrough in our ability to simulate not only the dark matter, which is easy, but also the visible part of galaxies, the ordinary matter, the 5% I was telling you about before. So this is still dark matter. This is a movie from something called the Eagle simulations that were carried out at Durham. Here now we see dark matter we've seen before, but now we can see the gas. Now the gas is different from dark matter. It follows the gravity of the dark matter. It falls onto those clumps, but gas can lose energy, and it's spinning, and so it ends up eventually settling into disks, like you will see in a minute. So here's a disk that formed again out of those quantum fluctuations of inflation that we cut to stars. The disks become unstable and produce stars, and this is going on as the universe evolves, not just in this galaxy we're going to pan out in a minute, and you see that many galaxies like this are being formed pretty much with the same relatively simple physics: gravity that produces the dark matter, gas that falls in follows the gravity of the dark matter, loses energy, settles into a disk. The disk then breaks up into stars, and you end up with objects like this. Here's a picture of the real universe, and here's images of galaxies. You can put the light back on if you want. So these are real galaxies. Now, I've actually fooled 1 or 2 maybe not very competent observational astronomers, asking if they know the numbers of these galaxies. They're not real galaxies. They don't exist in the universe. They exist inside the cosmology machine supercomputer at Durham. So they look a lot like the real thing. So this whole picture hangs together very well. And so to finish off, the reason I've given you all these, shown you all these slides is so that I want to give a little bit of believability to what I'm about to tell you. I'm going to tell you now at the distant future of our universe. What we can say with all certainty is that we do understand to a great extent how the universe became to be the way it is. Now, so this is another of my heroes, Thomas Wright of Durham, and he was the first, together with Immanuel Kant, to recognize the galaxies could exist. So 270 years after the idea of galaxies was first put forward, I think we now have a perfectly credible model of how those galaxies came to be, which is supported by the laws of physics and by empirical evidence. So what about the far future? Can we extrapolate to the far future? Now here is where, I'm going to go very quickly through this because it's pure speculation. I got this picture from Martin. This is a big warning sign that what I'm about to tell you may be me leaving the confines of respectable science and venturing a bit beyond. But it's interesting. It's the kind of thing that keeps people awake at night. Now, and we know quite a bit. We can make some educated speculation. The main thing we know is the far future of the universe depends on the behavior of the dark energy. Now, here are some two parts of our universe that are worth recognizing. Here we are, and here's a sphere around us. This is the visible universe. There's something called the cosmological horizon, which is the distance from which light has reached us since the Big Bang. So that's called the cosmological horizon. I didn't say that, but it was in one of my slides. The universe is 13.7 billion years old, but the cosmological horizon is much bigger because the universe has been expanding. So we can see out to 45 billion light years away. So that's called the cosmological horizon. There's another horizon called the Hubble radius, shown here in red, and that is the distance beyond which galaxies are moving away from us faster than the speed of light. Now, you might worry a bit about that, but of course, if galaxies are moving away from us and the expansion is accelerating, at some point they're going to exceed the speed of light and more. And that's perfectly okay with relativity because there's no transfer of information involved. It's just the space between the galaxies that is growing. So that cosmological horizon is then what divides part of the universe where galaxies are receding from us slower than the speed of light, and this is where beyond that they move away from us at faster than the speed of light. And I say there's no problem with relativity. Now, if the expansion of the universe continues to accelerate, then the cosmological horizon and the Hubble radius that I showed in red and the cosmological horizon will start shrinking because the expansion would cause more and more of the universe to expand faster than the speed of light. So the Hubble radius and the cosmological horizon will begin to shrink. And so we will be able to see less and less of our universe just because more of it, we cannot see anything that's expanding faster than light. And more of it is going to be expanding faster than light, so we'll see less and less as time goes by. So eventually, we won't be able to see outside our own Milky Way galaxy. And that's where, when I meet politicians, I tell them, this is the time to put money into astronomy. If you wait too long, we won't be able to see outside our own galaxy. So that now is the time to find out about our universe. So here are the possible three fates for our universe. And it all depends on the behavior of the dark energy. So there are three possibilities, and I'm going to describe them quickly, but I just want to say that we're not totally in the blind. In fact, astronomers can know quite a lot about the dark energy, contrary to what I was saying before. We don't know the origin, but we know we can characterize it. So the dark energy has something called an equation of state. It has a pressure and a density. It's a typical equation of state. In this case, however, it's weird because the pressure is negative, but this W is basically a way to characterize the dark energy. And the reason I'm showing you this is because we have three possibilities. One is that W is -1, negative pressure. That's Einstein's cosmological constant. But we don't know whether W is always the same or whether it changes with time. If it varies, it's something called quintessence. And if it's less than -1, it's something called phantom dark energy. You can see why I'm telling you this in a second. Point I want to make here is that these are observational data from a variety of sources, the cosmic microwave background and others. Here's this quantity W, and you can see that empirically we can actually measure what W is to some precision. So the best number currently is that W is -1 within a small error. -1 is Einstein's simple cosmological constant. It doesn't rule out that W could change tomorrow, but as far as we know, Einstein's cosmological constant is consistent with all the data that we see around us. So what's going to happen? Well, there are three possibilities. Let me first consider one that I think is the most unlikely, something called the Big Rip, which would happen if this W is less than -1. This is also called phantom dark energy. I say it's very unphysical, very unlikely, but I'll just tell you what would happen in the Big Rip. In the Big Rip, the acceleration is itself accelerating. So the expansion is accelerating at a faster and faster rate. So the universe goes wild. The horizon, I told you, would shrink. In the case of this phantom dark energy, would shrink to 0. There will be a singularity, and that's known as the Big Rip, where the universe will just tear itself apart. I think this is probably very unlikely. It violates all sorts of other things. I don't have time to tell you about it. So don't worry. I think the Big Rip is just physicists trying to find something interesting to say. Now, another alternative is the Big Crunch, which would happen if, contrary to what phantom energy, if the acceleration, if the dark energy begins to decrease, if the acceleration it slows down a little bit, then eventually the universe will stop expanding. It would reach a maximum size, and then it would collapse onto itself, and it might start again. So a universe could be cyclical if this dark energy, in fact, changes with time, but changes in such a way that it becomes less important as time goes by. Now, some people, for aesthetic reasons or philosophical reasons, like this sort of universe. I don't particularly like them that much, and I have a brief movie, that will show you why. So here's a cartoon, an animation of what the Big Crunch would look like. So here we have galaxies. We reached maximum expansion already. They're all coming together, and look what's going to happen. So everything will become really dense. There'll be enormous tidal fields, as we call them. It won't be the Big Crunch a place to be hanging about if it does happen. Now, as far as we know, the future of the universe will be determined by, as far as we know today, by the simplest form of dark energy, which is Einstein's cosmological constant, the one I mentioned earlier. As I said, all the evidence we have is that that is what our universe has today. And in that case, what will happen is that the expansion will just continue and continue and continue forever. And now, all sorts of things would happen. I have a timeline here. I not have time, so I've run over time already to give you all the things that are going to happen. We already know 1 billion years from now, the sun luminosity will increase and the oceans will boil. We know that. About 8 billion years from now, the Earth will fall into the sun. All sorts of things will happen. 100 billion years from now, it's 100 billion, so don't worry. Still time to think about it. All galaxies in the local group would merge into a super galaxy. The horizon will shrink, become smaller than the local group. All sorts of interesting things will happen. Eventually, galaxies will begin to disintegrate. Atoms will disintegrate if protons decay, but a long time from now, the whole universe will become black holes, but even the black holes will themselves evaporate by a phenomenon discovered here in Cambridge by Stephen Hawking and Malcolm Perry called Hawking radiation. The universe will be full of radiation. All that will be left is a dilute gas of radiation and some simple particles. And eventually, in a long future, 10 to the 105 billion years from now, the universe will approach an equilibrium. There'll be nothing, there'll not be black holes, there'll just be radiation, but the radiation will have reached what in thermodynamics we call the maximum entropy state, and then nothing more will happen because it's called the heat death of the universe, and if you don't have entropy, it's very difficult even to talk about time. So even the arrow of time might disappear. So here I've really strayed into fantasy, And there's no better form of fantasy than poetry. So I think this state is better described in the words of T.S. Eliot. This is the way the world ends. This is the way the world ends. This is the way the world ends, not with a bang, but with a whimper. But there's a sting in the tail of this whimper, because if the universe lasts long enough, there'll be a quantum fluctuation somewhere that could produce a new Big Bang, that will produce a new universe. In fact, the universe hangs around long enough, this will happen many times. So in spite of this heat death, new universes might appear, and they will do their inflation themselves, and there might be many more of these universes, what string theorists like to call the string theory landscape, or the multiverse, where in all these little valleys, there are universes that are completely separate from others. They cannot communicate with others. The laws of physics might be different, but the universe, in fact, might be, or the multiverse, much richer than what we think it is. So let me conclude then. So I started by telling you about the Drake equation. We started off locally in the solar system, and I told you that there are two unknowns in Drake's equation, the fraction of inhabited planets that have intelligent life. And I'm agnostic about this. I didn't realize until recently that it takes quite a bit for intelligent life to emerge. You have to have quiescent evolution, unless intelligent life keeps appearing for billions of years, and that state is not that easy to find. And the other unknown is the lifetime of civilizations. If civilizations are short-lived, then we may be the only civilization in the universe today. But if it's not, there could be millions of them. But our descendants better move off our planet within the next billion years or so. So in the second part, I told you that we now have a standard model of cosmology that gives an amazing account of a lot of the data that we see. The future is uncertain. The indications today is that the universe will just continue to expand forever, maybe spawning new universes as it goes along. So here is how I'd like to conclude, namely with one of my favorite pictures, the Garden of Earthly Delights. Here is hell, and I think the big rib belongs to hell. Here's paradise. Maybe the cyclic universe appeals in some way. It's kind of heavenly in some way. But here we're on Earth in the most likely outcome, which is Einstein's cosmological constant. Humanity, or civilization, has decided to invest vast amounts of money in trying to figure out what of those alternatives is the most likely. We have investments of lots and lots of money, billions in various instruments, some of which are already operational. And of course, we have the power of computers that immensely enlarge the power of the human mind. So let me finish with a picture of Durham Cathedral. Here I just say that there's been tremendous progress in cosmology in the past 30 years, but there are still very big questions to be answered. Are we alone? Where is everyone? And where, not where, but how will it all end? And at least my lecture ends here.